Hello, my name is Nevell and I'm here today to give a quick talk about my thesis topic and basically the planning stage of it. My thesis topic is the thermal performance analysis of a process industry, and the industry I've chosen is a vapor power station. So if you'll please turn to slide 2. Right, a quick project definition and scope. Basically I'm trying to investigate the thermal performance of a vapor power station. For this I'm going to develop a computerized model using some software. And this model is going to be used to analyze and optimize the performance of the system. Data from a reference plant is also going to be received, and this data is going to be compared to the model to validate the model, and also just to basically have a second source of reference along with some hand calculations. After the model is optimized and some changes have been put in to hopefully improve the thermal performance, these improvements are then going to be justified and pretty much given to the client. Okay, so some benefits of the investigation. There's a large number of vapor power plants all around the world, and so increasing the thermal efficiencies of these is something that is quite wanted, because there's a lot of benefits to it and it's really viable around everywhere in the world. There are other cycles that currently exist, such as combined Brayton-Rankine, Rankine geothermal, Rankine solar, or Rankine organic cycles, but these aren't always viable in all places due to the environment and other possibilities such as capital expenditure. So basically we want to try and optimize the performance of the current Rankine cycle that's implemented all around the world. We'll do this by both changing some of the parameters of optimization, such as the temperatures, pressures, flow rates, and enthalpies, to see what changes that makes. And we will also try and investigate some new system configurations, such as additional feed water heaters. The great thing about this is, if we can get this to work and get a better thermal performance, then it will really decrease the amount of fuel required, and this can help both the environment and economically. It helps the environment by decreasing emissions and also the actual mining of the fossil fuels required. So if you can please turn to slide 4. Right, project deliverables. We've obviously got the model that we are going to create and optimize, and we've also got data from reference plants that I've already said that we're going to change to validate that with. There's also going to be a comparison of the reports, and there's going to be a justification of the changes that we propose and why we think they will increase the thermal performance of the vapor power cycle. After this, of course, part of the thesis will have a full report of findings in a technical paper, and also a technical poster and presentation will be given to my engineering peers. So if you change to slide 5, limitations we have are we can't analyze every single little aspect of the vapor power cycle because it is quite complex, and this basically means we're not going to analyze anything to do with the current fuel source and its combustion. We're also not going to analyze anything to do with the cooling tower and condensing water cycle. All our proposed improvements will also only be from a conceptual point of view, and they won't be ready for a full design. And finally, it will not be a transient analysis of the system, but only a steady state. This also means that startup and shutdown won't be considered, and just the primary operation of the cycle. If you please turn to slide 6. Righto, so this is just a quick slide showing the methodology and work breakdown of all the different tools that I've used to plan out my implementation stage of my thesis. I'll go through each of them now. If you turn to slide 7. Alright, so selected software. I chose Aspen Plus as my selected software after reviewing a number of different ones in my literature review. This was due to its flowsheet setup that I found allowed for a really easy development of the model. Changes to the model can also be made quite easily because of this. This program's flowsheet setup also allows for a lot of equipment to already be just pretty much ready to drag and drop in, such as turbines, pumps, heat exchangers, all sorts of stuff we're going to be using. The software also contains all the properties of working fluids, such as water, which we'll be using, so that saves a lot of time, and also it cuts down a lot of potential for mathematical error if programs such as Simulink were used, where equations would have to be researched and the model would have to be, the validation process would be a lot more intense and a lot harder to work out if everything was working correctly. If you'll please turn to slide 8. Okay, so this is just a Gantt chart that I've done up of the implementation process. It's quite small on the slides, but I have a detailed workdown if you'll turn to slide 9. Righto, so in that Gantt chart, we've got some major tasks, and these are broken down even further. If you want to look at it closer, it'll be in my project folder. Basically, the first thing I'm going to do in implementation is familiarize myself with the Aspen software. It's important because if I don't know what I'm doing with the software, then there's no way I can create the model. This will have a lot of research and just a creation of a basic Rankine model before I try and complete the one that's actually accurate to the Vapour power plant that's being modeled. After the development of this model, we will then have to validate it. So this is where we'll compare the hand calculations and also the data received from the reference plant. Once this is all done, we can start actually trying to optimize performance. Firstly, we will mess with some of the parameters, such as temperatures and pressures, to see how that changes the thermal efficiency. And then we'll also try and implement some new equipment, such as additional feed water heaters, more heat exchangers, and maybe mess with some of the feed water heaters so that they're either closed or open and see what changes that make. After that, and all this is done, obviously the results have to be communicated, and this will be done through a technical paper, poster, and oral presentation, and also a reflected paper, and Engineers Self-Assessment will be, Engineers Australia Criteria Self-Assessment will be done as per required by the thesis. So if you'll change to slide 10, here's just a risk assessment of the project. So pretty common stuff like project running over schedule and limited access to software. So we've done a Gantt chart to plan it, and we've made sure we can get access to the software, and it's what we want right away. Data acquisition, I've already contacted a reference plant, and they've pretty much given me most of the data I need already, and I've ensured that I can get everything I want. And model functionality problems, this is why I have such a long period of time planned, that I can learn the program and lots of time to validate the model so that we're not pushing for time. If you'll turn to slide 11. Right, just some assumptions. Water will be used as the working fluid, and the properties given by Aspen 1 will be assumed to be close enough to the properties of the actual water. The data supplied by the reference plant obviously has to be assumed to be accurate, and there are no potential mistakes made with their readings. The theoretical formulas in the literature review section also have to be deemed to be accurate enough, even though there are some assumptions made in each of those formulas that's identified. Any minor fluctuations in performance over a long period of time are neglected, as we're only doing steady-state analysis. And once again, start and shutdown is not being modeled. Pipework losses, like heat losses through pipes, they will either be considered negligible if they're small enough, or they'll just be lumped into one big sum and considered for the whole system. Also, all individual components of the cycle will be analysed using control volumes and be considered black boxes. And yeah, all minor components will be considered negligible and not analysed. If you'll turn to slide 12. So my governing equations are based off the laws of thermodynamics and energy balance. There will also be temperatures, pressures, flow rates, and enthalpies calculated at each principal state of the cycle. Then thermal efficiencies of the Rankine cycle will be found, and also the backwork ratio. And finally, the concept of available energy will be used to try and optimize the performance further. If you'll turn to slide 13. Right, so this just has some reference plant data. This is the heat balance sheet. You probably can't see it very well on the slides, but it gives you their design temperatures, pressures, and flow rates and everything of the plant, and how the working fluid flows through each piece of equipment and back to completing the cycle. If you go to slide 14, this is displayed in a bit of a similar way, but it's more from a control system. So it's basically the same sort of information displayed a bit differently. If you now go to slide 15, this is the temperature entropy diagram of the system. So it's very useful, as this is a very common thermodynamic analysis tool, and it also shows each point on the diagram, which is quite useful. If you now go to slide 16, so our model validation requirements, we're going to be using the concept of energy balance and the laws of thermodynamics. Obviously, there are basics, and from this we will be comparing with hand calculations that are done with our data that's extracted from the simulation. We'll also compare with hand calculations done for a Carnot cycle, which is the ideal cycle. So if our model says that our thermal efficiency is higher than this, then obviously we've got a problem, but it's just a quick way of telling if we're in a plausible area. We'll also be comparing with our data supplied by the reference plant and what they believe their thermal efficiency is at. And finally, we will just be basing it off previous research that will be done in the early stages into modeling Rankine cycles and feed water systems to ensure that no major mistakes have been made that could critically throw off the accuracy of the model. We'll now turn to slide 17. Right, so model optimization criteria. We're going to be working with the properties of the working fluid at each state, previously mentioned, such as temperatures, pressures, flow rates, and enthalpies, as these are already known to change the thermal performance. So we will be trying to optimize these in the simulation model. We'll also be implementing the concept of available energy, which has been discussed in the literature review, and it's based off the second law of thermodynamics and often considered a much better way of working out thermal performance over just common thermal efficiency, which is based off the first law. We'll also be focusing on individual equipment's thermal efficiency, specifically ones that are found to have lower thermal efficiencies, as it's known that if we can increase the thermal efficiency of each equipment without changing others, it will increase the overall efficiency of the whole Rankine cycle, which is what we're aiming to do. And then finally, we'll be trialing different equipment configurations and changing some of the parameters of current equipment, and then justifying all of our optimization choices on a variety of different parameters, such as some minor economical, capital, business, and environmental considerations. Yeah, so that's, if you turn to slide 18, that's pretty much my project. Thank you for listening.